Good morning and welcome to the almost 7th video session on chapter number 5, that is multimedia authoring and data representation, from the subject multimedia communication technique, final year electronics and telecommunication engineering, Solapur University, Solapur. Now as I told, it's almost 7th video, so let us quickly look back. We have seen the previous point from this video in on different video sessions for introduction to multimedia and hypermedia, the difference, the application of hypermedia, that is World Wide Web, overview of multimedia software tools. Now here we have seen several software tools which are used for different kinds of medias. Then we have seen image and graphic data representations. In that we have seen two kinds, like what is the different image types. It could be 1-bit gray image, 8-bit gray scale image or monochrome image, then 24-bit color image and 8-bit color image, which is the compressed version of that. And then we have seen in the last video session related to the different file formats, like the GIF, PNG, JPEG. So all these different kinds of image file formats that we have seen. So today let us cover the last part of this particular chapter, that is color in image and video. In that we will specifically focus on color science, then the different color models for the video images, fundamental concepts in video and audio. Now, out of which fundamental concept of audio and video we have already seen in the first session, that what exactly and audio system is, what, like even in fourth chapter we have covered a lot about the audio, and in first chapter we have covered about video, how and video is been constructed, how and video basically is, which is the continuity of the different images, like continuity of the vision or persistence of vision with which the video is been captured and has been telecasted, broadcasted over the different television sets. So that is what we have seen about the fundamental concepts of audio and video. Now let us specifically focus on the color science and different color models for the video. Now it will take a bit because we have almost 59 to 60 slides. So in last particular session we have seen these many popular image formats, that is GIF, JPEG, PNG, TIFF, Windows BMP, Windows WMF, XF, PS and PDF, Macintosh Paint and PICT, graphic animation format, and X Windows BPM. So all these different glimpses of all these formats we have seen. Now let us stick ourselves to the next bit, which is nothing but the color science. Now before we go ahead with description of the color science, we must know what exactly, how do we see, like how do we visualize the things. Now whenever we try to see through a sensor to our body, which is nothing but the human eye, so whenever we try to see what exactly happened or what is the science behind it, like whenever we try to see an object, basically the presence of the light, it may be a natural light or any artificial light, but presence of light is very, very important, so that whenever certain light source has been used, that light source will be strike that particular object, and there will be certain light which will be reflected from that particular object, and it will strike the human eye, and then we try to see that particular image with the eye and the brain coordination. Like if we know about that particular object, we will immediately recognize that, and then the things will work out in progress. Now when we talk specifically about the color science, like we got to see or we got to revise a bit, like about what is the difference between the monochrome and the color. So what we have seen about monochrome is it is an one-dimensional signal. That means whatever the light comes, we can have a category of that particular light which varies from completely black to a completely white. Like it can be scaled down. Like if we try to scale it down with an 8-bit signal, so we can scale it down from 8 zeros to 8 ones, or if we need to represent it, then it could be like from 0 to 255. So that way we can recognize that particular signal if it is an black and white signal, or if it is an monochrome signal. So a monochrome signal is a single dimensional signal, so that it can be scaled down or it can be recognized with a single amount of value or single amount of signal. While if you look for color, then color signals, so infinite amount of color signals are there. So if we decided, like if we wish to give a different signal for a different color, such millions and trillions of certain signals will be there. So let us try to understand like how human eye recognize it, and what are the different cones that are present in our human eye, and how basically it works. So let us talk about light and the spectra. So light is an electromagnetic wave, and its color is characterized by the wavelength of the wave. So basically light is an electromagnetic wave which has certain, like when we talk about the visible spectrum, then it will have certain wavelength, and depending upon that, like if you recall, like when you were a kid, then there used to be certain experiments where you have used a prism, and whenever you pass certain light, then there will be certain lights coming out of that particular prism, and all of them will lined at a specific distance. So depending upon wavelength of every individual color, there will be a spectrum came out of that particular prism. So this way, if we scale it down over and a scale of on x-axis, let us say we have considered a wavelength, and on y-axis if we consider the spectrum power, so it will look like a graph somewhere similar to this, where on x-axis we represented between 400 to 700, which is nothing but the visible light spectrum, and on this axis, on y-axis, we will have the power related to the spectral distribution. Now when we talk about an human eye, it basically works like a camera with the lens focusing on an image onto the retina. So whenever certain light from that object will hit back to the human eye, it will sense by the lens which is in forward side, and at the back of it the image will be imprinted on the retina. So the retina consisting of array of rods and three kinds of cones. Now basically, though we say here three kinds of cones, basically there are millions of cones, but specifically these three cones will be very, very sensitive. These receptors are called such because they are shaped like cone and rods. The rods came into the play when light levels are low and produce an image in shade of grey. For higher light levels, the cones each produce a signal because of their different pigments. Three kinds of cones are most sensitive to red, green and blue. So that is the reason why right from the beginning of this particular chapter or syllabus, entire syllabus we can quote, like we continuously talk about the primary colors, that is RGB value. That reason is like there are almost 6 million cones which are present in human eye. Out of that, these are the most sensitive cones, which are nothing but R, G and B, from which we can derive the maximum amount of signal. Like here you can see in this particular graph, where maximum amount of throughput which is given by is from the green, and then the red, and then the last one will be the blue. So the eye is the most sensitive to light in the middle of the visible spectrum, and where the value of color came is nothing but the G and R. Additionally, we have added R, additionally we have added the value B, which is almost in the leftmost corner. Then The eye has about 6 million cones, but the properties of R, G and B cone are different. They likely be present in the ratio of 40:20:1. Now these spectral sensitivity function are usually denoted by some other letters than R, G and B, which is denoted by the vector called Q of lambda. So this Q of lambda, the equation has already been given here. Then there are three sensors, and each is of a function of wavelength. Now if you look for here, now when we look for the green color, red color, the blue color, each of it has a different wavelength, and these are the primary color with which we can obtain any kind of color. Now when we go for the different color models, like as I told you right beginning from this particular subject, we are talking about primary colors. We are talking about the combination of the color to represent any of the color. So the first model itself came forward, which is normally how we look or how we recognize one particular object in our human body itself. Like it is based on the additive mixture, which is nothing but based on the percentage values of R, G and B, and that is where the first color model which is suggested is nothing but the RGB color model for CRT displays. Now all light sensations to the eye are divided into three main groups. The optic nerve system then integrates the different color impressions in accordance with the curve which is shown in the figure. Now this is the cone which is shown in the figure. We have already seen this cone. To perceive the actual color of the object being seen, this is called as additive mixture and form basic of any color television system. So what basically it is trying to say is, with the help of the additive mixture of all these three color cones, we can represent any of the color which is available. So in additive mixing, which forms the basic of color television, light from two or more color obtained either from independent source or through filter can create a combined sensation of different color. The additive mixing of three primary colors, that is red, green and blue, is in adjustable intensities can create the most of the colors encountered in everyday's life. So this is how an RGB color model work, which is the basic principle of operation is based on the additive mixing, where any color which we can observe, which we can use, which we can see the regular day-to-day life. So most of them, almost 95-96% of all those colors can be obtained with the help of this RGB color cones, and that is why it is one of the most famous and mostly used model, that is nothing but this RGB color model. Now nothing but the subtractive color model, which is also called as CMY color model. Now what we have seen till now is the additive color model, where we use the three cone, which is nothing but the RGB cone, where to form any color we ensure that any two or all three colors will be added together to form the required color, and that is how we see that particular color. But in subtractive mixing, instead of focusing on the additive nature of the color, we focus on the reflective properties. So in what happen exactly in subtractive mixing is, the reflecting properties of pigments are used, which absorb all the wavelengths excluding their characteristics color wavelength. So what exactly it does, it absorb whatever the object is there. Let us consider a case where a white paper is there, and on which if you try to put some drops of any color, so what will be happening over there is, that particular paper is going to abstract or absorb all the other colors, but it is going to reflect the characteristics of the color with which it has formed. So what exactly happened here is in extractive mixing, the reflecting properties of the pigments are used, which absorb all wavelength, all other wavelengths it will absorb, and it will reflect the characteristics color wavelengths. Now if you get confused here, let me quote one simple example. If on a white piece of paper, if you drop certain yellow, if certain drops of yellow color, then basically yellow color is made up of red and green. So red and green are the characteristics color for the yellow. Then what exactly it does is, whenever certain yellow dot fall on the white paper, then what happen is the yellow ink will subtract the blue color, which is nothing but, because blue is nothing to do with the primary color characteristics of the yellow color. So yellow, blue's contribution is 0. So for yellow color, the characteristics color wavelength is definitely not blue. So what it does is, it will reflect that particular, it will absorb that particular wavelength, which is not there in the characteristics color wavelength. And that is the reason why whenever you drop yellow, then blue will be absorbed, and which is the characteristics color, which is nothing but red and yellow, red and green, that will be reflected back. And when those two color reflected back, those will strike the human eye, and the combination of red and green will appear as a yellow. And that is how the working principle of subtractive mixing is. So I'll read this again. In subtractive mixing, the reflecting properties of pigments are used, which absorb all the wavelengths, excluding, it will absorb all other wavelength excluding their characteristics color. Let me quote another example. If red color dots are fall on the white sheet, then the green and blue color will be absorbed and red will be reflected, so that reflected color will strike the human eye and it can recognize the color is red. And that is how this subtractive mixing color model, that is CMY model, is all about. When the pigments of two or more colors are mixed, they reflect wavelengths which are common to both. Since the pigments are not quite saturated, which are not pure in color, they reflect fairly wide band of wavelengths. While in additive mixing, that is what I told earlier, that in additive mixing, when two colors beam hit the target, like take example of the CRT screen. So when two color beams, say take a same example of yellow, so green will be striking and red will be striking its own dot, like we have seen in color model, in color television model, like there will be 3 phosphor dots, phosphor dot for red, phosphor dot for green, and phosphor dot for the blue one. So each color beam will strike that particular phosphor dot, and then the common dot will eliminate. So here for yellow, the green and red will strike the red and green dot, and accordingly it will eliminate in common as yellow. So in additive mixing, when two color beams hit the target, their color adds. When two phosphor dots on when two phosphors on CRT screen are turned on, their colors add. So for example, red phosphor plus green phosphor makes yellow light. But for ink, let us take example of how subtractive mixing work. But for ink deposited on paper, it in essence of opposite situation holds. Yellow ink subtracts the blue from white elimination. So as I told, whenever certain yellow color is made to hit the white background, white paper, then the yellow ink subtract blue from the white elimination, but reflects the green and red. That is why we see, or that is the reason why it appears as yellow. Now this is what the comparison between the RGB and CMY color cubes. Now here you can see in RGB model how this the center area, the beginning area here is marked with the red, then blue is here and the green is here. So three axis, which we can say x axis as green, y axis as blue, and then z axis as red. And then accordingly, when all of them meet here, or when all of them are at 0th position, when all of them are at 0th position, 0 0 0, that means absence of all three colors at origin, we will see here a black color. And when all three are present, all three are having the highest value, that 111 value is there, that is where R, G and B both are present, that means we will see here white color. And then depending upon who is mixing with whom, we tends to see different colors like yellow, then we see cyan, then we see magenta. So that way, like combination of red plus blue, here we get magenta, then the combination of blue plus green, here we get cyan. Here we have the blue and green combinedly get we cyan, and then green and red combinedly we get here yellow. So that way the CMY cube, how it will appear like this, where we have on x-axis here magenta, we have on z-axis as cyan, and here yellow is there. So this is how the block is just tilted a bit. In both the models, absolutely the things are going to one and the same only, with little change in the concepts. So obviously when we have gone here for inversions, or we have gone here for subtraction way, so origin we will be getting here as white, and the highest point here when all three are present, that we will be getting here black. Now let us move towards the next color model, which is nothing but the transformation from okay, just a minute. So we have seen this. Now what exactly it happened in subtractive color model additionally is, in CMY model, that is cyan, magenta and yellow color model, instead of red, green and blue primaries, we need primaries that amount to red, green and blue. We need to subtract R, G or B. These subtractive color primaries are cyan, magenta and yellow, as shown in color cube that we have seen earlier. The diagram, RGB and CMY are connected. In additive, the ROB system, the black is no light, and RGB value that is 0 0 0. And in subtractive CMY system, the black arise from like subtracting all light by laying down the ink, which is nothing but C is equal to M is equal to 1, that is when all are present. So that way this is what we have seen here only, that is the origin point of RGB, RG and B. Now if we go for the transformation, if you want to go for changing the one images from one model to another model, how we go for this transformation here. So as we know, those are exactly the inversion model of one and another. So this is how the inverse transform that we took to convert the color model from one to another. So given identification of role of ink in the subtractive system, the simplest model we can invent to specify that what ink density to lay down on paper to make a certain desired RGB color is as follow. This is how the inversion took place. Then the color model for video. So we have three different color modules. Actually in color television system we have three different in analog color television system we have three different kinds of color system that are available. That is the PAL, NTSC and CCAM. Now based on these three modules only, we have two color models in video. So probably in the next video we will look into that, but for that we need to study the preliminary how the PAL and NTSC work, because both these models, like hardly only 2 bits are left, but both these models are completely based on how the PAL and NTSC works. So we will in the next session we will take the revision of PAL and NTSC first, so that understanding of these two color models will become much more easier. Now next session will not be much elongated, because only few concepts are left. So maybe by next video session we will be done with the chapter number 5. So thank you till now. Stay safe. Thank you.